Okay, Dr. Smith here. I'm going to try to go through the answers to this review worksheet that I've put together. So here we go. First problem is about Mr. Culbertson getting all confused at TJ. So I assume you read this. This is important. It's especially important for my students because we haven't done any of these graphing problems in class. So this is really your chance to work out on a graphing problem and see if you can do it right. So I recommend you try to do this yourself and then compare your answers to mine, and only consult this when you're done or when you feel like you need a push. So anyway, to start with, question A, what is Mr. Culbertson's velocity at t equals 9.0 seconds? So question A, this is one of these sort of deceptively simple problems. We're trying to find velocity. This is a velocity versus time plot. So you just go to 9 seconds, which is right about there, and you read off what the velocity is. And I would say the velocity there, I don't know, 5.0, maybe a little more. Velocity is about 5 meters per second. So high. So let's see, then question B, find his instantaneous acceleration at t equals 11 seconds. So let's go up to 11, and I will try to get a different color here. Let's see, ooh, colors. Green, okay. So here is 11 seconds, and we want to find his instantaneous acceleration there. So how do we find acceleration from a velocity versus time plot? It's the slope. If you remember the little hierarchy of plots for one-dimensional kinematics, you go position, velocity, acceleration. These are all versus time, okay? And to go down, you take the slope. So to go from velocity to acceleration, I didn't really leave room to draw it, but to go from velocity down to acceleration, you take the slope, and then to go up one step at a time, really, so it's more like this, you take the area under the curve. Okay, so anyway, right here, we've got instantaneous acceleration at t equals 11 seconds. So we want to find the slope at this one point, which means we draw a tangent line. So I don't really, I think most of us are pretty tolerant on what we consider an acceptable tangent line. This is probably worse than what most of you will draw, but I would call this good enough. So let's do that and find the slope of this. Let's see, it looks like we're going down to almost to -2 and almost up to 6. So really call it like 5 to -2. So acceleration at 11 seconds is going to be the slope of this. So I'm going to say this is a rise, or it's a rise of -7. So we're going from +5 down to -2. Close enough. I mean, it's a little bit above both, right? But -7 meters per second. And then the horizontal between our 2 points is 8 and 14. So that is 6 seconds. So this is going to be approximately equal to -1.1, 1.2 meters per second squared, give or take. Okay, and again, I'm not really picky about where these things come out. As long as you're drawing a reasonable tangent line, you're showing me that you know how to do this problem, you're fine. So let's try a different color for C. Find his average acceleration between t equals 16 and t equals 22 seconds. So here's 16 and here's 22. Find average acceleration. We don't take a tangent line, we take a secant line. And you can remember this by remembering that a secant line is 2 points, right? And a tangent line is 1 point. If we ask for average acceleration, we're giving it over some period. We're giving you some period and asking for the average acceleration over that period of time. And we have to then give you 2 times to use, a beginning time and an ending time. This is my rough guess at a straight line. I'll learn to draw straight lines in Sketchbook at some point. But for now, this is what I've got. And so, anyway, so a secant line intersects at 2 points. So when you have 2 times given and you're asked for an acceleration, or anything that will ask you to find the slope, and you're given 2 different horizontal points, then you're probably taking a secant line, right? And when you're only given 1 point, you have to take a tangent line, because that's the kind of line that intersects at 1 point. Okay, so I'm going to say our average acceleration is then given its rise over run. I'm going to write it as delta V over delta T, Okay, so your delta V between here and here, let's see, you're ending at negative 11 meters per second and you're starting at 0. So negative 11 meters per second minus 0. Okay, and then your delta T, you're ending at 22 seconds. 22 seconds, and you're starting at 16 seconds. So this is going to be negative 11 meters per second over 22 minus 16 is 6 seconds. Sorry, my S's are missing their upper strokes. Now it looks like 65. 6 seconds. Sure, that's great handwriting there. Okay. So acceleration, average acceleration is going to be, well, it's negative 1 5/6. So call that like negative 1.8 meters per second squared. Okay, give or take again. All right, let's find a new color for, well, I'm running out of colors. So we'll go back to blue. For number 4, what is Mr. Culbertson's displacement from the door at the end of the period shown? So now what we need to do is find, I'm going to take like a purpley thing there. We need to find area under these curves, because to go from velocity to displacement, you take the area under the curve. So let me try something here. Awesome. Okay, I'm just going to bring in a whole new, crap, if I can, okay, there we go. Bring in a whole new thing so that I can do DEF. Perfect. Okay, so now I'll get my pen back, and we should be good. Okay, so for D, we want to find the area under the curve, because that's how you go from velocity to position. So I'm not very picky as far as what I consider a valid area. So however you want to do it, I'm going to do like this, roughly, triangle like that, and then maybe go like that. And I'm just sort of guessing here that the area I'm missing here is made up by the extra area I'm taking here. It's not exact, but again, I don't care, and I don't think any of the physics teachers will care if you're precise or not, as long as you show that you understand what you're supposed to be doing. So these two areas here that I've outlined in this sort of pinkish purple are the areas I'm going to look at. And again, I'm horrible at drawing. Even on paper, I'm horrible at drawing. And so this is even worse. So I want to find the areas of these two triangles. So the area, actually I don't want to write A because that's A. So delta X here is going to be the area for this guy, is going to be the area of this triangle. So I'm going to find this. And it's going to be 1/2 of the base of the triangle. So 1/2 times, I'm going to say about 15 seconds. And then the height of the triangle is 1, 2, 3, 4, but that's actually 8 meters per second. Okay. So now that gets me 60 meters. Okay. Now for the bottom part, we take the area, right? So I'm going to go ahead and do that. That's for this guy. And 1/2 base times height. So 1/2. The base here, I'm going to say, is 5 seconds. And the height is, let's see, 11. Okay. 11 meters per second, which gives us 1/2 to 50.5, 27.5 meters. Now, have I done this all correctly? What about the sign? Remember, displacement is a vector, so it's got a direction, and the direction is, tells you whether you've been displaced in one direction or the other. And the sign is, when we're doing 1D kinematics, the sign is the direction. So here, Mr. Culbertson's got a positive velocity all through here. So this here represents a positive displacement. Okay, so it's positive. Here, he's going in a negative direction. So this represents a negative displacement. Now, so this should be a negative 27.5. Now, one way to sort of handle this is to just say, okay, well, it's area below the curve. If you really want to understand how to make this work, though, or you want to sort of understand this on a slightly deeper level, what you can say is the base of this triangle is still 5 seconds, right? But the height of it, well, it points downward, so it's actually a negative height. So this is really negative 11 meters per second is the height. So what I'm going to do here is add these together and say that for the total trip, he goes forward he goes in the positive direction 60 meters, and then he goes back the other way 27.5 meters. So total displacement is going to be 60.0 minus 27.5, which is going to be 32.5 meters. So positive 32.5. I'm just going to leave it like that and say positive is default. So there you go. That's part D. The displacement is positive 32.5 meters. Part E, at what point or at what time? Oh, let's go for like orange now. Okay. So we want to know what time is he furthest from the door, and how far away is he then? Well, here he's going in one direction, right? He's going away from the door here in the positive direction. So if you think like here's, you know, the positive x-axis, okay? Positive x. Trust me, it's positive x. Here's 0. For this whole first bit, up through at the end of that triangle, he's going this way, and he goes about 60 meters. And then here, he starts coming back. So he comes back this way. So right here, before he turns around, is when he's furthest from the door. So I'd say probably, he's still going forward here and a little bit forward there. So I'd say probably 16 seconds. Okay, so answer to E, at what time is he furthest from the door? I'd say at T equals 16.0 seconds. And how far away is he at that time? He's gone 60 meters, right? This is before he starts to come back. So 60.0 meters. So there we go. F, what's the total distance he walks or runs during this period? Well, he goes the 60 this way, and then he turns around and goes back 25. And that's his only change in direction, right? So he's going forward here, then he turns around and goes backwards. So you just add these two distances up, add the absolute values, and you'll get the answer for that. So let's go back to green, I guess. So for F, we're going to have total distance is, he's going to go 60 meters plus 27.5 meters. And so he's going to go a total of 87.5 meters. Again, these are approximate. If you get slightly different numbers, that's fine, as long as you're doing it correctly. G, average velocity and average speed. So these are not hard. Average velocity, we just apply our definitions here. So for G, I'm going to do G down here. Average velocity is displacement divided by elapsed time. And let's see, so it's 24 seconds, right, passes through the whole period. And its displacement is 32.5 meters. So 32.5 meters divided by 24.0 seconds. And that's going to be, I'm not going to figure this out exactly, but it's going to be a little bit more than 1.3. So approximately 1.35 maybe meters per second. Again, this depends on what you pick. And it's positive because his total displacement is positive. Okay, and positive divided by positive is, of course, positive. Okay, and so this is average velocity. And I'm writing V average as average velocity. Average velocity. Okay, and then for the other part, average speed, you take the total distance. Average speed equals the distance he went divided by the time, and that's going to be, I'm totally scrawling here now, but 87.5 meters, 87.5 meters divided by 24 seconds, which is going to be, let's see, 72 and then 15-ish, so 1.65, no, sorry, 3.65, so roughly 3.65, give or take, meters per second is his average speed. So there you go. That's the first one.